the presentation, but I should give a very brief, I'd like to give a brief introduction to Suzanne Carbotte and background to the presentation, but I also want her to have the full amount of time to show the really exciting science that she's doing. So just very briefly, Suzanne did her undergraduate degree in geology and physics at the University of Toronto, and then moved to Queen's, where she did an MSc in geophysics, working with Professor Edward Ferrer. At that point then, she moved to the University of California, Santa Barbara, where she started a PhD with Ken McDonald, and completed her PhD in '92. Immediately after that, then she went as a postdoctoral fellow to Lamont Doherty Earth Observatory, where she is now the Hazen senior scientist at LDEO. Now, one additional, well, some of you know Suzanne well. I thought I would search a bit for an amusing anecdote to introduce her talk, and I had to do huge amounts of research because Suzanne is amazingly clean, I think, in terms of history. But I was privileged to receive an interesting email from Ken McDonald, who pointed out that in one of Suzanne's first research cruises on the East Pacific Rise, they were towing a deep camera and additional equipment, and Ken said, you're a bit too conservative and a bit too safe. Tow it a bit deeper. Come on, Suzanne, take a few risks. I mean, it's exciting science. Maybe we'll find a black smoker. Well, Suzanne towed it a bit deeper, and she created her own by knocking off the top of an inactive black smoker, which immediately started gushing. And so Suzanne has her own black smoker. She can create her own. So I don't think she'll be creating her own subsurface structure today, but she'll be focusing in on mid-ocean ridge segmentation. So, Suzanne, thank you very much.
Thank you.
Hey, I did my trick, too.
Okay. All right. Today, I'm going to be giving an overview on some of the new insights we've gained about mid-ocean ridge segmentation from recent studies in the last 5 to 10 years. These new insights are arising from the growing availability of global data sets, increasingly multidisciplinary studies that are being conducted in focused areas along the mid-ocean ridge, and from new capabilities for high-resolution studies. I'm going to be focusing on the fast-spreading ridges, where with the greater, faster rates of crustal creation, the greater rates of the tape recorder formation, key processes are preserved in greater fidelity. Also at the fast-spreading ridges, where a mantle upwelling is believed to be more sheet-like, two-dimensional, the origin of segmentation is perhaps more actively debated. So this is a perspective view of the East Pacific Rise, looking north towards Central America here in the distance. The ridge is offset by a number of transform faults as well as smaller non-transform discontinuities, and a large number of smaller third and fourth order discontinuities that span a hierarchy of segmentation. I'm going to be focusing in particular on the East Pacific Rise between Siqueiros and the Clipperton transforms. As a result of the focused investigations in these areas, this is arguably the one place along the mid-ocean ridge where we can now relate the superficial architecture of the mid-ocean ridge all the way through the shallow crust, mid-crust, all the way to the shallow mantle. And spanning this full range of the length scales of segmentation. I'm going to be presenting results, some of my own work as well as the work of others that bears on the origin of each of these length scales. Okay, so general outline of the talk. I'll give a brief introduction, scales of segmentation, key characteristics. Then I'm going to talk briefly about the tectonic segmentation and evolution of the EPR 8 to 11 North segment. And then I'm going to talk about magmatic segmentation, recent observations, and implications across the different spectrums of segmentation scales. So, segmentation, the global significance of ridge segmentation. It's linked to processes of melt generation and mantle flow associated with plate motion, so it's telling us about mantle dynamics. The segmented structure that's inherited from crustal formation defines the basic 3D architecture of the oceanic crust. Segmentation controls the location, geometry of fluid pathways in the crust and into the mantle, where water, so it's controlling where water is getting in, very important for subduction processes and production of arc magmas. It's relevant for understanding segmentation of continental rifts, and many aspects can be better studied in a marine setting. It's seismic imaging of magmatic systems is more readily done using marine techniques. And it defines the architecture of hydrothermal fluid flow in the crust, which supports the deep biosphere potentially linked to the origin of life. Key characteristics. We find segmentation present at all spreading rates with important variations in style. Segmentation is present on different length scales from hundreds of kilometers to a few kilometers, bounded by distinct classes of tectonic discontinuities of the ridge axis. Segments are associated with variations in ridge properties that indicate segmentation in mantle melt production delivery to the ridge axis. And key among these are seafloor structure, crustal magma distribution, lava geochemistry, along with hydrothermal characteristics of the ridge. Okay, so very, very quickly, the largest scale segmentation is defined by the transform offsets. Transforms remain stationary along the ridge for millions of years, defining a stable segmentation. They offset the ridge by tens to hundreds of kilometers, corresponding to age contrasts of millions to tens of millions of years, depending on spreading rate, and they're believed to have a significant thermal effect in the mantle. Now we're zooming into the finer scale second order segmentation defined by these, at both fast and slow spreading ridges, by these non-transform discontinuities which are observed to migrate along the ridge axis, indicating that at these scales segments can lengthen and grow and disappear. The processes by which these segments evolve is not well understood. These segments offset the ridge by these discontinuities offset the ridge by typically 5 to 20 kilometers, corresponding to much smaller age contrasts of hundreds of thousands of years to up to maybe 1 million years at the slower spreading rates. And these discontinuities are not believed to have a significant effect in the mantle. Within the second order bounded discontinuities, we find a third order scale of segmentation. At the slow spreading ridges, it's defined by these on echelon volcanic ridges that are found within the Rift Valley of the Mid-Atlantic Ridge. At the fast spreading ridges, it's defined by changes in the volcanic morphology of the ridge axis and changes in the trend of the ridge axis. This segmentation is believed to be to persist for only tens to hundreds of thousands of years, although the duration of this segmentation is not well established. Okay, so in the early 1980s, mid-1980s, when this morphologic segmentation of the ridge axis was identified, variations in a variety of ridge properties along the ridge axis were recognized, from which variations in magma supply to the ridge from the mantle were inferred. So key ridge properties from which this magmatic segmentation was inferred included undulations in the systematic undulations in axial morphology, axial depth, changes in the distribution of magma in the crust, and changes in lava geochemistry. So this is an axial depth profile from the East Pacific Rise. This is roughly 1,000 kilometers along the ridge. These are seafloor depths picked along the ridge axis. And we see undulations in depth at several length scales, with the discontinuities located at these deeper points along the ridge axis. Assuming isostatic equilibrium for this topography, these depth undulations indicate differences in the integrated density structure of the underlying crust and mantle from which variations in magma supply have been inferred. We also found from early studies that the distribution of magma detected in the crust varies with this segmentation. This is a compilation of results for roughly the same length of the East Pacific Rise, showing the depth to the seafloor, much lower vertical exaggeration here, but also in red here, where a magma lens reflection has been detected in seismic studies conducted along the mid-ocean ridge. So this is an example seismic profile from this segment of the ridge, roughly 70 kilometers long here, showing this bright reflection that we commonly see in multi-channel seismic studies at the fast-spreading ridges, believed to arise from a thin sill of fully to partially molten melt that sits atop a broader region of crystal mush believed with a few percent melt. So this is readily imaged in multi-channel seismic studies. And what we're seeing is at the larger discontinuities, the magma body, magma reflection typically disappears. At the smaller discontinuities, we typically see steps in the depth to this magma body. And then variations in lava geochemistry along the ridge axis were recognized early on. These variations were found at a very fine scale, much finer than the large tectonic discontinuities of the ridge. This is a figure from Langmuir et al. 86, showing variations in several geochemical parameters from lava sampled along the East Pacific Rise, again, roughly the same stretch that we were just looking at. The discontinuities are indicated with the vertical bars. The transform faults are these bold lines here. You can't decipher this variability very well. So I've plotted on the right-hand panel the barium-titanium ratios from this data set for the length of ridge between Sikeros and Clipperton, showing that the small overlapping discontinuity is a chemical boundary separating lavas with very uniform barium-titanium ratios from a suite of lavas on this southern segment with higher values, these being barium-titanium ratios being an indicator of source compositions, mantle source. Okay, so the models for the origin of magmatic segmentation fall into two general classes. They're not mutually exclusive, and strong feedbacks between these two classes of models is believed to be operating in the Earth. The two classes of models are basically origins lying in the plate versus in the mantle. So the plate models include segmentation arising due to changes in plate motion. Feedbacks between amagmatic extension and hydrothermal heat loss are likely to be very important, particularly at the slower spreading rates. The mantle models for segmentation include 3D mantle upwelling due to, for example, gravitational instabilities in the upwelling mantle, Rayleigh-Taylor type instabilities, source heterogeneity. 3D melt delivery is another of the other of the important mantle-based models. This 3D delivery due to melt segregation and transport, for example, through veins, channels, and dye piers. Okay, building on these mantle origin models for magmatic segmentation, this is a schematic illustration of this model of central supply beneath each of the different length scales of segmentation along the ridge with a long axis flow away from the sites of central injection from the mantle, with the discontinuities forming at these regions, at the distal ends of these centrally supplied regions, with the implication that magma supply is reduced at these discontinuities. So new studies that have been conducted in the East Pacific Rise 8 to 11 North area allow us to test a number of aspects of this magma supply model and implications for the origin of segmentation. As I mentioned earlier, this region encompasses the full spectrum of scales of segmentation observed. The 8 to 11 North segment is offset by two major transform faults. There's a second-order segmentation defined by this overlapping spreading center discontinuity that has a history of southward migration over the last few million years. Then a third-order segmentation defined by these changes in trend of the ridge axis, and a finer scale segmentation. In the next few slides, I'm going to give an overview on the tectonic history of this region over the last 10 million years. Okay, this is a magnetic anomaly compilation from Euler et al. 2008. The current active plate boundary is shown in the bold line. In the thinner black lines are 1 million year isochrons. We see that this Clipperton to Siqueiros segment initiated approximately 9 million years ago with a clockwise change in plate motion. Clipperton existed prior to that time as a major right-stepping offset, but Siqueiros initiated at that time. Since then, we've had a counterclockwise change in plate motion since roughly 3 million years ago. This is illustrated in a schematic from Lonsdale, 1995, from his analysis of magnetic anomalies. At around 3 million years, we see the ongoing northward propagation of the East Pacific Rise, spreading ceasing on the mathematician ridge. Between 3 million years and the present time, we've had spreading ending on the mathematician ridge and development of the Rivera transform fault. This reconfiguration of the plate boundary in the last 3 million years has resulted in a counterclockwise change in plate motion that has has acted to place Clipperton, which is a right-stepping offset in compression, and has acted to give rise to opening along the left-stepping Siqueiros transform. We see development of a series of intertransform spreading centers since this time along Siqueiros, and we see development of compressional ridges along the Clipperton transform. At the present time, the major first-order segments north and south of the Clipperton to Siqueiros segment are oriented roughly 4 degrees counterclockwise from the main Siqueiros to Clipperton segment, and it appears that transpression across Clipperton is constraining the ability of the Siqueiros to Clipperton segment to respond to the plate motion change. But when we look at the very fine-scale volcanic segmentation along this ridge, We see it's made up of a series of on-echelon segments oriented 347 to 351, so counterclockwise by several degrees to the regional trend of the ridge axis. So we see in this region segmentation down to a very fine scale that's organized in response to this counterclockwise change in plate motion. So now I'm going to turn to the magmatic segmentation of the ridge in this area and the new observations. I'm going to look at each of the different length scales of segmentation, and I'm going to begin with results of a study we presented a few years ago focused on the asymmetry in ridge structure that we observe across discontinuities. So this is the depth profile I showed you earlier, but here I want to draw your attention to the marked asymmetry that we're seeing in ridge morphology, ridge depth here across the discontinuities. We very typically see this is a ubiquitous pattern along the fast and intermediate and much of the slow-spreading ridges, where we see changes in ridge elevation across these discontinuities with one segment consistently shallower than the adjoining segment across the discontinuity. So the next slide is going to be a blow-up of bathymetry for the two ridge segments north and south of Clipperton. So the map on the left here is the ridge axis south of the Clipperton transform. The map on the right is north of Clipperton. We see markedly different ridge morphology and flank morphology. The ridge south of the transform fault is broad and shallow, almost right to the ridge transform intersection. North of Clipperton, the much narrower ridge axis, which steadily deepens and plunges towards the transform fault over a long distance of 60 kilometers. This steady plunging of the transform cannot be attributed to a of the ridge axis cannot be attributed to a transform cold edge effect, because such effect would be expected to be symmetric across the transform, and that is not observed. We see an asymmetry in magma distribution within the crust across the transform. Again, this is a blow-up of the compilation from seismic imaging of the magma body beneath the East Pacific Rise that I showed you earlier. Here, the ridge axis south of Clipperton, we're detecting a magma lens in the mid-crust, almost right to the ridge transform intersection. But north of Clipperton, we don't image any magma body for 70 kilometers from the transform fault. We see a marked asymmetry in other ridge properties. Here, gravity anomalies across the transform faults. This is results from Greg et al. 2007 showing residual mantle-Bouguer anomalies. So here the gravity anomalies have been corrected for the predicted effect of on mantle densities of the age contrasts across the transforms. And we're seeing here low residual mantle-Bouguer anomalies are in the blue colors, and we're seeing marked asymmetry across both of these transforms with lower values indicating lower densities in the crust and mantle at the southern ridge transform intersection compared to this northern one. So we looked at these asymmetries in ridge properties across discontinuities in the context of plate kinematics and find a consistent correlation with the direction of migration of the mid-ocean ridge with respect to the underlying mantle. The map on the left here is the East Pacific Rise, showing the configuration of the plate boundary from roughly 3 to 18 north, encompassing the Clipperton to Siqueiro segment here. This is the corresponding axial depth profile. Transform faults are indicated with the bold arrows, and the thinner lines correspond with the smaller discontinuities. We're seeing steps in ridge elevation across all of these discontinuities. All of the mid-ocean ridges are migrating with respect to the underlying mantle in the absolute motion reference frame. The white arrows here are the migration direction of the northern East Pacific rise calculated from the absolute plate motion model of Grip and Gordon. So the East Pacific rise is migrating to the northwest. And when we look at these changes in ridge elevation across the discontinuities in the context of this migration direction, we find that the shallow segments are consistently those segments that are stepping in the direction of ridge migration across the discontinuities. So they're the leading segments. And I've highlighted those segments that are leading across both bounding discontinuities with red here. So these are these anomalously shallow segments along the East Pacific rise. We see the same pattern at other intermediate and fast-spreading ridges. Here is a map showing the Gorda-Juan de Fuca ridge, the plate boundary configuration here. The ridge is migrating to the northwest. Major transform offset here, the Blanco. We see the southern Juan de Fuca ridge across Blanco over a kilometer shallower than the ridge axis, the trailing ridge axis to the south. Spreading rates are comparable along the northern Gorda as along the Juan de Fuca. Again, the Sovanco transform, southern Explorer ridge, almost a kilometer shallower than the trailing Endeavour segment to the south. Here is a segment of the Pacific Antarctic ridge, a fast-spreading ridge. This is roughly 1,000 kilometers. And I'm highlighting, again, with red, the segments that are leading segments along both their bounding discontinuities, and they're consistently shallow relative to the adjoining trailing segments. So this is a compilation from 15,000 kilometers of the global mid-ocean ridge. That's almost a quarter of the global mid-ocean ridge system. These are from fast and intermediate spreading ridges. I've plotted here the axial depth asymmetry across the discontinuity as a function of discontinuity offset length, and grouping here all segments where the leading segments are shallow and all cases where the trailing segments are shallow. We're finding the overwhelming majority of cases lie in the field of leading segments shallow. For 85% of the transform faults, 75% of the non-transform offsets. We see a very interesting pattern of these differences in ridge elevation across the discontinuities actually diminishing at the larger offset transforms, a similar range of depth asymmetry at the smaller offsets as at the intermediate length transforms. So this is the conceptual model we presented to account for these observations. Building on early studies of Davis and Karsten and Schouten in the mid-1980s, simple kinematic considerations predict that upwelling should be asymmetric beneath a migrating ridge with faster upwelling, greater melt production beneath a leading, beneath an advancing plate. If melt is pooled towards the ridge over some finite volume, which at the ends of ridge segments will include the upwelling zone of the adjoining segment, as leading segments will then be tapping from the upwelling zone of the faster melt production zone of the advancing plate. We have a mechanism to generate asymmetry in the melt that's drawn to the ridge. So this conceptual model is supported by numerical modeling of Katz et al. 2004. Assuming a pressure and temperature dependent viscosity for the mantle, they calculate the melting rate perturbation due to a migrating ridge, which is shown in this bottom figure here. And they're showing here a marked asymmetry in the melting rate perturbation with higher rates beneath the advancing plate. They parameterize melt migration, assume focusing by buoyant flow along a thermally imposed impermeable barrier. They then look at an idealized melt pooling region and calculate the expected asymmetry in isostatically supported ridge elevation across a discontinuity as a function of the offset length of the discontinuity. Their model results are shown in this slide here. This is offset length on the horizontal axis, predicted difference in axial depth on the vertical axis. The different colored lines here correspond with different spreading rates. And they calculate a variation with offset distance that's qualitatively similar to the observed variation, with the prediction that depth anomalies should disappear for offsets greater than the width of the melt production zone. Okay, so with, from that largest scale now, I'm going to focus in on the second order segmentation, what we're learning from the studies of the two ridge segments bounding this 903 discontinuity. There's two main observations I want to highlight. One are the results from recent seismic studies on the distribution of melt beneath these two segments, and the other is the observation of anomalous crustal production associated with, over a very wide region, appears to be associated with the migration and evolution of this northern segment that's marked in this V-shaped wake of this discontinuity. So beginning with the first melt distribution in the mantle beneath these second-order segments, this is the seismic undershoot study of Toomey et al. Showing variations in low velocity zones found beneath the ridge axis from their undershoot experiment. This is a map of the bathymetry and their experimental layout. This is let's see, we see here the lower velocities are in the warmer colors and the higher velocities are in the cooler colors. And what this study shows is a series of discrete closed contour lows beneath the ridge axis at a roughly 15 to 40 kilometer scale. We see that the mantle melt distribution is offset at the discontinuity, the 903 overlapper. The ridge axis is indicated with the dashed black line here. So this is the OSC. But we see no indication that melt supply is reduced in this area, and we see no indication of, no evidence for central supply to these two segments with redistribution at shallow mantle levels towards the segment ends. The other observation from segment scale studies in this area is of a broad region of anomalous crustal production that's associated with the evolution of this northern segment. So the map on the left is crustal magnetization, showing a broad region of more highly magnetic rocks forming a V-shaped that's centered on the discontinuity located here, and indicating the southward migration of this discontinuity over the past million years. The next figure from Canales et al. 2000 shows crustal thickness variations in this area derived from the undershoot experiment. Here, the thicker crust is in the darker grays, thinner crust in the lighter grays. The ridge axis, where they had no coverage, is highlighted in white. And we see here a region of thicker crust that lies behind this V-shaped region of more highly magnetic crust, which I've highlighted with the white lines here. The next panel is residual gravity anomalies computed assuming this distribution of crustal thickness. And it shows here the cool colors correspond to higher gravity anomalies. It shows a region of higher inferred density that coincides with this region of thicker crust that lies in behind the more highly magnetic crust. Here, the black line is centered on, passes through the mantle low velocity zone that coincides, that's the on-axis projection of this region of denser crust, thicker crust associated with this second order segment. So what this is telling us is that the evolution of this segment over the last 1 million years, the lengthening of the segment, does not involve just local processes at this discontinuity. We're not looking at dike lengthening due to the small age contrast across this discontinuity to account for the southward migration of this lengthening of this segment. Rather, we have anomalous crustal production on a segment scale that's associated with this long-term segment evolution. Okay, now I'm going to turn to the finer scale third-order segmentation within this region. And the main observation I want to emphasize here is that we now recognize that this is the fundamental volcanic segmentation of the mid-ocean ridge, and that it's inherited directly from the shallow melt distribution at the base of the crust. We have 8 to 9, depending on interpretation, third-order segments within this region. This is a map of the northern 3 of those segments. And again, we're identifying this segmentation based on the fine-scale volcanic morphology of the ridge axis, as well as the trend of the ridge. The map on the right-hand side, I've highlighted the ridge trends for these 3 segments. The yellow stars indicate the locations of the discontinuities. When we look at the ridge flank fabric, we can trace this discontinuity on the ridge flank out to crust roughly 300,000 years, indicating the segmentation has persisted for that long in this area. We find this volcanic segmentation of the ridge is also present in variations in lava morphology and hydrothermal vents and biological communities along the ridge axis. The figures on the left are from White et al. 2002, showing variations in lava morphology from 908 to 956 along the ridge. We're seeing, these are histograms of pillow lavas and lava domes, and we see these morphologies preferentially found at these discontinuities between the third order segments. The figure on the right is from Heyman and White, 2004, showing variations in the number of hydrothermal vents and the biological communities found along the ridge. The red arrows indicate the third order discontinuities, and we see that the hydrothermal vents, biological communities, are preferentially found within the centers of these segments. When we look at this third order segmentation defined by the superficial architecture of the ridge, and we map it to the distribution of low velocity zones in the shallow mantle as imaged in the Toomey et al. Study, we find an excellent correlation between this third order segmentation and the distribution of these mantle low velocity zones. These define segmentation on ranging from 15 to roughly 40 kilometers. This is a similar length scale of segmentation as we're inferring from the geochemistry as well as structural studies of in the Oman ophiolite. So this is a figure taken from Monnier et al., building on studies also of Blumet et al., 2004, showing spinel chrome number, which is an indicator of extent of melting, from a whole suite of samples that they've collected along the Oman mantle peridotite extending roughly 200 kilometers here. And they see two different length scales of variation, one at 50 to 100 kilometers corresponding to our second order or transform bounded segmentation, and then they see a shorter length scale of variations in this extent of melting on the 10 to 20 kilometer length scales comparable to this third order segmentation we see on the East Pacific Rise. A controversial result of the undershoot experiment is an apparent skewness in the orientation of mantle flow relative to the Nouvelle 1 plate motion spreading direction. This mantle skewness is inferred from the azimuthal anisotropy of the PN travel times and is indicated with the green arrow here, the preferred orientation. The black arrow here shows the Nouvelle 1 spreading direction, and there's a 9-degree counterclockwise offset between these two orientations, which Tumidel suggests may be playing an important role in segmentation within this area. However, when we look at the orientations of the first order segments north and south of Clipperton, as well as the orientations of this third order segmentation, which is defining the active spreading direction within this region, we find that it's, these orientations sit roughly 348, and there appears to be relatively little skewness to explain. Okay, so now I'm going to focus on the finest scale of segmentation, and I'll be presenting some early results from a 3D multi-channel seismic study which we conducted this summer. This fourth order finest scale of segmentation is defined by very small offsets in the narrow depression that's found along the East Pacific Rise that is believed to mark the locus of most active volcanism and most of the hydrothermalism. This narrow depression it's imaged here in ultra-high resolution bathymetry from Fenari et al. It corresponds to this feature here. I've lost my mouse. On the maps in the middle and on the left here, I've highlighted the walls of this summit depression taken from Sewell et al. In a black line. And we see very small changes in the structure of the summit depression or small steps in the location of this feature on the order of a couple hundred meters that define a segmentation indicated with the red arrows here. The yellow stars here indicate the location of the third order segment boundaries, so we have a number of fourth order segments within each of these third order larger scale third order segments. And this finest scale segmentation has been believed to be fairly quite ephemeral, maybe perhaps governed by lateral dike intrusions. The northernmost of those, the fourth order segments I was just showing you, is the site of two volcanic eruptions that have been directly observed on the mid-ocean ridge, the only place on the mid-ocean ridge where we have these observations of eruptions. The first occurred in 1991, and the movie that played very briefly was showing flocculent bacterial material emanating from the seafloor immediately after this eruption. The extent of that eruption in 91 is indicated here with the red bar. This area erupted again in 2005, 2006. Basically the same region erupted, same seafloor expression. The outline of the new eruption is known in much greater detail due to bottom photography studies that were conducted during several cruises after this eruption and analyzed by Sewell et al. The bottom photographs here show the new 2005 eruption, lavas overlying the older lavas, as well as here the fresh lava encasing an ocean bottom seismometer from Tolstoy et al., which was found to be still talking to an interrogating ship and later recovered. Okay, this region is also the site of most abundant hydrothermal venting along this stretch of the East Pacific Rise. Venting is found to be within two main clusters, and remarkably, this hydrothermal venting persisted in the same locations through the two eruptions that happened. So after the first eruption, we observed hot fluids emanating from toppled sulfide structures or straight from fresh basalt, but in the same locations where these high temperature vents were previously known to be occupying. The stability of the location of these hydrothermal vents through these two eruptions indicates relative stability in the hydrothermal flow paths in the subsurface. Okay, so this summer we conducted a multi-channel seismic study of this finest scale segmentation. We made use of the new National Seismic Facility, the Marcus Langseth, and conducted the first academic multi-streamer survey. This is the location of our track coverage. We were imaging most of this third-order segment as well as a number of these fourth-order segments defined by the red arrows. This is a schematic of the seismic configuration. We towed four 6-kilometer-long streamers. We had two linear gun arrays firing alternately to give 8 CMP lines for each sail line of data acquisition. The resulting, we acquired a total of 111 sail lines, corresponds to 888 CMP lines. This is roughly 4 times the total number of ridge crossings from all of the seismic studies we've conducted at mid-ocean ridges prior to this time. And with this great data density, we've observed much greater heterogeneity than we anticipated. Preliminary results were presented yesterday in poster session yesterday morning by Mutter et al., Canales et al., Nadimovic et al., Carton et al., and myself. This is our long axis profile from 9, basically from the overlapping spreading center discontinuity here up to the Clipperton transform. This is the seafloor here. We can image fairly well the base of seismic layer 2A, and then this is the bright reflection from the axial magma lens. And we can see at this scale there appears to be significant heterogeneity in the magma lens event, much more than had previously been appreciated from the older seismic data collected in this region. So the area of our 3D coverage corresponds to this box here. And so this is the box within which we will have very good resolution of the heterogeneity. This is a close-up of that area. And we're finding that the magma lens is not a continuous structure as previously assumed on these kinds of length scales, but rather is divided into a series of discrete magma lens events. We see changes in the depth of the magma lens. We see edge diffractions in this along axis view. We see changes in the amplitude of the event, small changes in depth. The next slide, I'm going to show you a series of cross-axis lines corresponding to this location here. So we're going to go over this discontinuity here. Without the dense coverage that our 3D provides, we would never be able to confidently interpret this variability. We wouldn't be able to rule out imaging artifacts. But we can see from the cross-axis lines, these are going from north to south over this discontinuity. The two northern lines, we have a relatively simple waveform here in the long-axis view. Here in cross-axis, we see a typical diffractive AMC reflection event. Another simple event on the next line to the south. On the third line, as we're crossing this region of complex waveform, we're picking up two magma lens diffractive events in the subsurface, and they're offset, looks like they're offset at their apex by roughly a kilometer. When we project the location of these discontinuities from our seismic profile onto the map view, the white arrows here correspond to the locations of the discontinuities identified in the magma lens, and the red arrows correspond with the locations of discontinuities identified morphologically from the surficial structure. We see an excellent correspondence indicating that these fine-scale variations in the summit trough are inherited from this magma lens segmentation, and they're not resulting from lateral propagation of dikes in this area. As I mentioned earlier, hydrothermal venting in this region is clustered. We see two distinct clusters. Each of these has experienced a distinct geochemical evolution over the 15 years that we have long time series monitoring measurements for. We've had very little information on the subsurface architecture of hydrothermal flow at mid-ocean ridge systems. We don't understand what controls the distribution of these hydrothermal vents, why they're found in some locations, why they're absent in others. I've plotted here in red the locations of these two vent clusters superimposed on our seismic profile, and we find that these two clusters are actually each associated with a discrete magma lens, indicating that this segmentation in the hydrothermal system is inherited from this segmentation in the heat source that's located 1.5 kilometers below. The extent of the eruption in this region is indicated with this green line here, so that's the extent of the new lavas found on the seafloor. We infer that these two lenses here were potentially involved in this eruption. And we find that the amplitude of these two lenses is markedly lower than the amplitude of the reflection event to the north and south. These amplitude variations presumably linked to differences in the melt content in the magma lens. So it appears that the eruption has been associated with draining of magma from the melt lens relative to the lenses to the north and south. We have an opportunity in this area to compare the new data that we've just collected with a pre-existing data set collected in 1985. This is a portion of the stacked section along axis from Kent et al. 1993. And remarkably, we find that this fine-scale segmentation, which we identify in the new data, was also present in the older 1985 data. And we've had two eruptions in the intervening time period between when these two snapshots were taken. So I'll draw your attention with the red arrows here to the this part of the magma lens here, where we see a southward dipping portion with a relatively horizontal region to the north. This is the same segmentation that we're observing in the 2008 data. So this very fine-scale segmentation is persisting through multiple eruptions. Okay, and finally, I'm going to talk just a little bit about geochemical variability in this region. It was observed early on that lava geochemistry varies on a very fine scale along the mid-ocean ridge, but seismic studies conducted along the same portions of the ridge showed an apparently continuous magma body underneath the ridge axis on length scales of tens to many tens of kilometers, leading to conflicting views from the geochemistry and the geophysics on the size and connectivity of the magma body under the ridge. The East Pacific rise from 9 to 10 north has been very densely sampled by Perfit, Sims, and colleagues over the last 15 years. This is a map showing MG number from very closely sampled lavas, spatial scales of hundreds of meters. These are samples taken within a kilometer of the ridge axis, and we're looking at MG number with the more primitive lavas in the reds and the more fractionated lavas in the cooler colors. So we're seeing fine scale variability along this stretch. And when we compare this variability with our magma lens segmentation, we find an excellent correlation here. The white arrows indicating the magma lens discontinuities projected onto the map view. And we're seeing that these individual magma lenses have apparently delivering to the seafloor lavas of fairly limited range of MG number, and that these steps in geochemical compositions are coinciding with our magma lens discontinuities. So, to summarize some of the new insights we're gaining from fast ridges, we find the geometry and motion of the ridge axis relative to the underlying mantle is contributing to large-scale segmentation. Melt tapping across discontinuities may play an important role at fast and intermediate ridges. The evolution of second-order segments involves anomalous crustal production on a second-order segment scale. It's not a localized process associated with the discontinuity zone itself. The evidence favors multiple sites of magma injection beneath first and second-order segments rather than central supply. The current snapshot that our seismic studies provide indicate there's no significant lateral redistribution of melt in the crust or in the shallow mantle. We find that these axial volcanic segments that are 20 to 40 kilometers long define the basic 3D architecture of the ridge, and they're inherited from segmentation in the melt distribution in the shallowest mantle. The crustal magma lens is segmented at an even finer scale and controls the distribution of seafloor eruptions, hydrothermal vents, biological communities located at the seafloor 1.5 kilometers above. And this segmentation we're seeing is persisting through multiple eruptions, setting the timescales for the seafloor volcanic, hydrothermal, and biologic system. So I'm going to end with an attempt to summarize these observations in a schematic for comparison with the previous magma supply model. We're finding, we're recognizing now marked asymmetries in ridge structure across discontinuities, with melt tapping across discontinuities possibly contributing. We're finding that this third-order segmentation is inherited from melt sitting at the base of the crust, the distribution of melt at the base of the crust. We're finding multiple sites of melt injection from the mantle beneath these second-order segments, not central supply. We don't have any evidence at these shallow levels for lateral redistribution of melts. And then we're finding the very finest scale segmentation is inherited from melts within the crust. That's it. Thank you.
Thank you.
Thank you, Suzanne. I think there are a few in the audience who appreciate the amazing courage it took to be the first to test out the 3D seismic system on the Marcus Langseth and to show so much and see so much. It is really very exciting. So thank you. And here's, there's time for a few questions. If I can identify from the audience. Are there any questions? Yes. Okay, let me repeat the question. Sorry, I'm just going to repeat the question. The question is, do you have evidence for lateral flow? On other ridges, there is some indication that that's the case.
Yes. Definitely, we have evidence for lateral dike propagation, so that's lateral redistribution within the crust. At the Juan de Fuca, it looks like if there's a magma body present in the crust, sorry, the dikes initiate above where a magma body is located, and they propagate laterally away from to places where there's no magma in the crust. So that's true at Axial, also true at Endeavor. I think it's true at the ends of the fast ridge segments where we don't detect magma in the crust, that those are probably built by lateral dike propagation in the crust. The question of, that we don't see any evidence for lateral redistribution from this current snapshot that our observations provide. We have other indications, other parts of ridge properties indicate lateral redistribution, but maybe it's happening at a deeper level.
One more question? Mm-hmm. Yes. Yeah.
You talked about the difference in the height of the in the direction of the leading plate, which talks about the higher.
Melt protection.
Yes.
Yes.
Yes, the shallower segments are leading in this.
Yeah, and there's an 85% transform offsets. In the cases where it doesn't occur, do you know why that isn't?
That's a very interesting question. For the for the longest the very long transform faults, we don't see this relationship. That we see this relationship for the smaller second order offsets at all is quite remarkable to me, but yeah.
Well, thank you very much.